In that case, we will begin on the wonderful world of ordinary least squares regression. Simple linear regression refers to the fact that the models are linear in the parameters, and I'll get back to what that means. Simple has to do with the idea that we only use one single independent variable to tell us something about the behavior of one single dependent variable. A canonical example can be the relationship between sales and advertising. If you increase advertising, what might you hope sales will do?
Increase.
Ideally, right? Now, if you increase advertising just forever, without bound, do you expect sales to just continue increasing?
No.
Eventually they'll decrease, and besides, eventually the world will run out of money to spend on advertising for this one product. So you can only use the model for within a narrow range, and in terms of this class, within the range for which you have data. If you use it outside, you're extrapolating. And that's fine to some extent in the real world. But again, it's one of those situations where you have to be careful. You're operating in uncharted waters. We're going to discuss the least squares methods, in other words, how we come up with a regression line based on the data and explicitly removing our own judgment. We're going to estimate how well our model does in accounting for the data. That's what the coefficient of determination is for. Then we're going to look at assumptions, see whether or not assumptions are met, see whether or not the model does much of anything, and then we're going to look at what the residuals are going to tell us with regards to those assumptions. So that's the game plan. In practice, what we're going to do is put up a few slides on the overhead, then we're going to illustrate on the whiteboard, and confusion will reign for a while because regression can seem a little painful at first. So once we get into sort of a good chunk of theory, we'll start on a problem which we'll use to illustrate and give you nitty-gritty details of exactly what it is we're doing and why. The first question that I'm usually posed is why in the world do we need three separate equations to describe one simple idea? The simple idea being that there's a relationship between x and y. Well, first of all, we have two straight lines here. We have one thing that's not even a straight line. And in fact, it's kind of a complicated story. Assume that you have, I'm going to call advertising x and sales y. Now, assume that there's an average relationship between advertising and sales. Think of it as, say, advertising for Coca-Cola in Mexico. And if you set advertising at a certain value, you can figure out what you think should be the average sales. Now, even if you come up with a specific number, is that average number always going to be the actual sales when you set advertising to be that value? No, because there's idiosyncratic risk, right? You will have a tornado go through your distribution center. You will have the flu raging, or all of a sudden you'll be, one of the musicians you sponsor will make it big and, 14-year-olds just buy way too much Coke. All sorts of things can happen to change the actual sales. But in the population, sort of in the background, there is assumed to be a true relationship, a true line that describes the average sales given some advertising level. Can you observe this true line? No. Because this is assumed to be in the population. The only thing you can observe is data. So the question then becomes, well, how do you get data? This comes from, so this is the mean of y, or expected value of y, and that's just beta 0 plus beta 1 x. Now, beta 0 and beta 1 are unobservable numbers in the population, and hence we have called them What's that?
Random?
Not estimations. Starts with a P.
Probability?
Parameters, excellent. Those are parameters. They're numbers, we don't know them, they're not moving around, they're constant. Now, we will estimate them, but not with the actual beta 0 and beta 1. So how is it that if you have, say, set advertising right here, you end up with an observation that is not exactly on that line? Well, the reason is that something happens. Again, tornado, flu, successful advertising campaign, whatever, but something happens. What we assume is that if you set this as your advertising level in general, and this is then your expected sales, you will draw from a distribution of disturbances that push away the data somewhat from the straight line. This distribution is the distribution for epsilon, which is normally distributed with a mean of 0 and a fixed standard deviation. So again, the process is as follows. You fix advertising, or X. That means you start out from the line, then you draw an epsilon, and the data point is somewhere either above or below epsilon. So this is your data generating process, and it generates dots. It does not generate a straight line. So let's now assume that the dots are being generated. So every single one of these dots represents an advertising sales combination, right? For 1 month, we advertised for 2 million, we sold 120 million. Okay? Now, this green line and epsilon generated the data. You can see the data, yes? You can just go back and look at how much you advertised and how much you sold. Can you use this to tell me where the green line is? Exactly where the green line is?
You can tell about where the green line is.
Very good. You can tell roughly where the green line is, but not exactly. And that's why we need a second estimator. Or a second line, really. One estimator. So based on your data set, you can just by freehand put in a line. Not perhaps the straightest example in the world, but nonetheless, a line. Assume you take one particular observation. This was generated, let's call this x2. Let's say you generated a value x2 here, which gave you y2, and this distance then was epsilon 2. Now, that point is right here. The distance between, okay, so that's x2, this is y2. That difference, is that necessarily epsilon 2? Well, while we're pondering that, let's write down the equation for this red line. It's y hat, which the hats here indicate that they're estimates. Estimated line is beta 0 hat plus beta 1 hat x. and we can subscript that by i's as well, but we don't need to. Now, you'll notice that B0 and B1 are used as well. So beta 0 hat and beta B and B1 as well, I'm sorry, beta 0 hat corresponds to B0, those are the same thing. Beta 1 hat and B1 are the same thing as well. Regression has more parents, if you will, than anything I've ever seen. It was developed about 200 years ago, and then about 100 some years ago, agriculturalists got their hands on this tool. And they were trying to figure out crop yields. How are crop yields related to rainfall, fertilizer, depth of the plow, the acidity in the soil, the space between harrows. You know, there are all sorts of things that they're trying to figure out. And regression is by far the best tool, and still is to a large extent. Although now with GPS, it's a far more exacting science or methodology. But the problem for us is, because agriculture started, and then we had physicists get into the game, and just general statisticians, of course, were developing everything alongside, and so on and so forth. We sometimes have not just two symbols, we have three words that mean the same thing, or three phrases. Explanatory variable, independent variable, predictor. They all mean exactly the same thing. And usually, people just talk about x's, so those are. So, it's not like consensus is complete either. It's just that I've standardized on what I think is the most common, and then I also span the use of certain notation and words, and hopefully at least get you an introduction to the different phrases. But I wouldn't really call it an argument, because I had, shall we say, a discussion with an editor about what we should use to call the epsilon here. And he insisted that we should call that unobserved error. Fine. You can call it that if you want. For us, it's noise or disturbance. Okay. We can observe the y2 and the x2, right? We know that value, so we know where this point is, yes? Do we know where the red line is? Red line is the estimated line. The estimated line that you put where you want. So you know this distance, you can calculate it, right? Now, one question is, how did you come up with the red line? Or how did I come up with the red line? Well, clearly, I just made it up, right? I just drew something. The difficulty with that is, it's subjective. So if you present your, I'd have to say, so-called analysis, this was the approach, and to a room of 30 people, you probably get 50 opinions as to where the line should go. And you're kind of SOL in that case. So we need to come up with a way to just use the data to give us a line without any further impact or input from us. So, we know where the line is, we know where the point is. We define that to be E2, and this is error. Error is observable. In general, is y minus y hat. And we can do this for every single point here. Yes? Okay. Can we agree that this distance, well, let me just ask, what distance should this be if the line fits that data point perfectly?
0.
0. Okay. Is it possible to draw a straight line through all the data points? It'd be tricky.
Only if you have 2.
Exactly. Well, no, you could have more, but you'd have to be very picky about where they are. Now, so the size of this thing tells us something about the poorness of the fit, how badly our line fits the data. Is there a way for us to take all these errors and come up with a way to say, this is how badly our line fits the entire data set at once?
There should be.
There is. There are multiple ways, actually.
Is it distribution?
Distribution of what?
The error, so.
It has to do with distribution of error terms, yes. So, we've got all these errors, and they tell us something. We want them to be zero if the line fits the data perfectly, yes? So how can we combine all the errors to give us some overall measure of how badly the line fits all the data at once? How do you typically combine things?
By adding them.
By adding them, okay. So if we add up all the errors, the question then is, well, what do we do with that? For one thing, we can force that to be zero. For any intercept, we can choose a slope that makes that zero, and, well, let's see. For any slope, we can choose an intercept that makes that zero. So, that's not, it's not enough for us to move forward. We need something that we can work a little bit more closely with. So, if we try to force that to be zero, that's not enough. What would happen if we tried to minimize this thing?
It's becomes actual, closer to the actual line.
No. What really would happen is that this line would go up towards positive infinity. You'd be subtracting positive infinity, and your sum of errors would go to minus infinity. There is no minimum. So that's not good. We need something that has a minimum in order for us to minimize it, right? And the question then is, does it matter if the error is on the top side or bottom side? Do we care about the discrepancy, or do we just want the line to fit as closely as possible to the dots?
You want to minimize the absolute value of the error.
Okay, you're right. This works. The problem is, the absolute value function looks like that. So it's remarkably ugly right there. Can we come up with a function that plays the same role as the absolute value here, which is what?
So just throw a square in there.
Right, and what is the role the absolute value does play? It forces each error to be, exactly, contribute a positive amount to the quantity by which the line does not fit the data. So we use the square term. And this thing is incredibly important. So this is the sum of squared errors. What is the value of the sum of squared errors if all the points are on the line? Zero. And can it be negative? No. So we want to minimize the sum of squared errors, right? Make sense to everyone? Okay. This part usually doesn't make too much sense. You fix your data. It's important to remember that. Your data is now fixed. How can you change the errors at all? Exactly. You change the line. Right? You can just change the red line. Every time you change the red line, you're changing the errors, yes? Okay. So when you are changing the line, what are you choosing? What are you moving around? And? You're changing the slope and the intercept, right? Beta 0 hat and beta 1 hat. So when you minimize the sum of squared errors, what are you minimizing over? What are your variables now? The sum of squared errors is a function of beta 0 hat and beta 1 hat, right? When you fix your data. So we're minimizing over beta 0 hat and beta 1 hat. part that gets, where we do wave our hands vigorously because calculus has been removed from the curriculum. Imagine a parabola but in 3 dimensions. Oops. More or less. You can picture a pottery wheel spinning with a parabola shape, right? And if you drop one drop of water in that thing, and imagine there's no friction, will it be able to find the bottom?
Spinning.
No, stop the spinning, just keep it still. Will the drop of water find the bottom?
Yes.
Yes. And how will it know, so to speak, that it's at the bottom? Gravity. Okay? And when it's at the bottom, gravity can't let it move any further south, right? Any further down. The reason is, no direction will have a downwards component. Yes? Correspondingly, no direction will, at that particular point either, be upwards. You have a flat spot. Everybody remember that? When you find the maximum or minimum of a function of one variable, you set the derivative to 0 and solve. Now, we're setting 2 partial derivatives to 0 and solving. So it's the same idea. Just imagine that you have a sheet of paper or something below your parabola. That gives you 2 different partial derivatives, one in this direction, the other in this direction. So you now have 2 equations and 2 unknowns. What are the 2 unknowns?
B sub 1, B sub
Okay.
beta hat sub 1, beta hat sub 0.
Exactly. So we're solving for beta hat 1 and beta hat 0. I'm sorry, beta 0 hat and beta 1 hat. And it's important to remember that even if we don't go through all the printing. So when we minimize, we end up with 2 equations, and those are, this is the minimization criterion, these are the 2 equations. Those look somewhat ugly. They're not quite as bad as they look. The second one is particularly easy, because what it's saying is, if you plug in the average value of x, what should you get? If you plug in x bar, you're going to get
Y bar.
y bar. That's all that's being said in the second equation. Here we've just subtracted beta 1 hat x bar from the other side. So the second equation is pretty straightforward. The first equation, of course, is a mess, but it's simpler than it looks. Does everyone remember this animal? What was it, or where did we use it?
Variance.
Variance, yes? In fact, it's the total variation in x, and that's how we label it. Sum of squares in the x's. Correspondingly, we have the sum of squares in the y's. And we even have corresponding sum of squares of xy, or sum of squares cross products. have you seen this before?
Covariance or co-something.
Excellent, yes. Covariance or co-something. Correlation coefficient,
Yeah.
yes. Okay, good. It perhaps stands to reason that we're gonna use something like a correlation coefficient when we're talking about how two variables move around together, right? All right. None of those are terribly difficult. I know we've already calculated this once. I'm gonna do it again today because the first equation is actually just beta 1/2, the slope estimate, is the sum of squares xy divided by the sum of squares xx. That I can manage to remember. And let me make sure. Yeah, right. Oh, going backwards. Yeah. Okay, good. Questions on that?
So that says sum of squares x, y, divided by sum of squares x.
Yes. The total cross variation divided by the total variation in x. That's equal to the slope estimate. So at this point, I'm thinking we need to do an example. Any questions on what's on the board before we do an example? Before we start on the example? Because I need to erase. Sure.
So we started with the model, then we came to the equation and.
Right, we have to assume that this is what's true in the population. It gives us data, then we use the data to get us errors, right? But right now, all we've done is we've said, okay, put this here, right? Give us errors, come up with a way to judge how good our estimate is, this is sum of squared errors, minimize the sum of squared errors to get us a new set of parameter estimates. And now, we can use those parameter estimates to update our red line and move it again. Now, when we do so, and let's say you do so and come up with an ordinary least squares line, typically, especially on the final, I'll ask, so can you now choose to, more judiciously choose your slope and intercept to get a smaller sum of squared errors?
That is it.
What's that?
That is it.
Exactly, because it's almost a tautological question, right?
Yeah.
We minimize the sum of squared errors, so there is no way you can come up with a better, smaller number. This is the very lowest that function will go. Yes? Okay. Yeah. Not just yet. So, can I erase? Anybody want me to leave it? Okay. In that case, you're gonna need to make ready quite a bit of space. I need 11 columns. So, you can start on the left and move to the right. Most people end up needing to do this sideways, yes?
How did you assume that error is normal distribution? Is it an assumption or?
It's an assumption. It makes our life easier. In fact, you don't even need it for most things, but it's just doesn't cost very much to make the assumption. All right. So this is problem 63, at least in the 9th. And in the 9th, we are told that we think in a manufacturing process there's a relationship between the line speed in 3 feet per minute and the number of defective parts found during the inspection process. To test the theory, managers devised a situation in which the same batch of parts was inspected visually at a variety of line speeds, and they collected the following data. wind speed, yi is going to be the number of effective parts found. And we had 20, 20, 40, 30, 60, 40, which gave us 21, 19, 15, 16, 14, and 17 defective parts. As a first step, we calculate the sum and the averages. The sums to 210 with an average of 35, which we'll label x bar. And the y's sum to 102, averages to 17, which we'll label y bar. And if we also, on a separate page, perhaps draw this thing. We've got 119, 15, 16, 17. Okay. Does it look like that has a positive or negative slope? Negative. Okay, good. Roughly, where would you put the intercept?
23, 24.
Oh, where?
23, 24.
Okay,
Well, between 20 and 25.
okay, so 24?
Yeah.
Okay. So our guesses, the intercept, 24. Now, so if we take 24, how much will that drop when we get out to 60? Drops to, how much? 14, okay. So 24 to 14, there's a drop of 10 over a 60 increase in x. So the estimated slope, you would say, without doing any regression, would be roughly minus 10 over 60, or minus 1 over 6. Right? This just gives you some rough feeling for what you're going to do formally now. If you get a slope of, say, 5, that would be a problem, yes? If you get an intercept of minus 102, also a problem. Yes? Just by graphing, you really know where you should be going. Make sense? Okay. So, where are we going? Well, we're going first to calculate our two equations. And which one of our two equations has to be calculated first?
Second, second one,
Because,
is this the y?
no.
You have to calculate the first one because the answer to the first one's a variable in the second.
Exactly. The answer for the first one, the slope estimate, is part of the second equation. So, you know, in the second equation, you know y bar, you know x, oops, this is x bar. But you need to know the slope estimate in order to find the intercept estimate. So you definitely need to do equation 1 first. All right, so let's crank through. First, x minus x bar, 20 minus 35 is minus 15. And so that's 20 minus 35. And similarly, we get 20 minus 30 again, minus 15. 5 minus 5, 25, and 5. Yes? Yes?
Y minus.
No, it's X. It's a poorly designed X. Here's a poorly designed Y. So here we got 21 minus 17, that's 4. 19 minus 17 is 2, and so on.
You win.
Okay, so now we've got to square these things, right? Because we want to calculate the sum squared, sum squares the x's, sum squares y, sum squares cross products. So we take xi minus x bar squared, yi minus y bar squared, and xi minus x bar times yi minus y bar. Okay, so we've got minus 15 times 4 is, no wait, that would be the last one. We have minus 15 squared, that's 225. Yes? Okay. Give me a second. Write down some of these. And adding them all up gives us 1150, which we labeled with the sum of squares